So far, we have learned about the producer strains, that is, improvement of strains, in order to increase their efficiency and to increase the productivity. Second important component in fermentation is the medium optimization. So, to find out optimized conditions that are required for the large scale production of microbial metabolites by the producer organism. Followed by that, the next important concept to learn in fermentation is medium sterilization. So, we all are aware of the concept of sterilization. So, sterilization of media is one of the critical parts of fermentation process. If the medium is contaminated during the process of fermentation, it may lead to several consequences. These consequences are basically because of the entry of foreign microorganisms in the medium. These consequences leads to loss of productivity because the contaminant organism, it may overgrow the producer organism, or it may produce its biomass in excess quantity, thereby decreasing the percentage of the count of producer organism. So, due to which it leads to decreased productivity of desirable metabolite. Contamination causes severe problems in case of continuous fermentation. So, we have learned about the concept of continuous fermentation. So, the major threat in continuous fermentation is contamination that leads to the overgrowth of contaminant, and it will, in due course, it will displace the producer organism, ultimately decreasing the productivity. Contamination also leads to severe problems, severe product contamination. If the product, fermentation product, is cell itself, means cells as final product. These fermentations are called as biomass based fermentations. So, when the cells itself are the final cellular product, in such fermentations, contamination is undesirable. For example, in case of biomass based fermentations like single cell protein production, that includes production of unicellular algae, production of unicellular yeast, production of biofertilizers, and production of biopesticides. So, entry of foreign organism, it leads to the contamination of final preparation. The production of undesirable compounds by the contaminant may create severe problems because fermentation broth is a complex mixture of several chemicals, and if contaminant produces certain undesirable metabolites, then it increases the complexity of fermentation broth. More is the complexity of fermentation broth, more are going to be the problems during extraction and purification. That means extraction and purification process is going to be difficult. Certain microorganisms, contaminants, may degrade the finished product, means they are responsible for the production of extracellular enzymes that may degrade the compounds which are produced by desirable organisms. Say for example, in case of antibiotic fermentation, particularly in case of penicillin production, the bacterial contaminants like Bacillus, Staphylococcus, they degrade this antibiotic by means of production of an enzyme which is extracellular, called as beta-lactamase. So these bacterial contaminants are beta-lactamase producers that degrades the beta-lactam ring and inactivates the activity of that antibiotic. Contamination of bacterial fermentation with phages. So phages may be responsible for contamination. So phages as contaminants, it could result in the lysis of the culture of the producer organism, and again it leads to decrease in the cell number of producers and decrease in the productivity. There are several ways by which the contamination or the entry of foreign organisms in the fermentation medium avoided. So there are several ways. First one is the use of pure culture or pure inoculum at the start of fermentation. So utmost care has to be taken in order to prepare the inoculum. It should be free from undesirable contaminants. Sterilization of medium. Sterilization of fermentation vessel. Sterilization of all the additives which are added in the fermentation broth during the incubation period. For example, there may be additives like, to control foaming, there may be addition of anti-foam agents which should be added in sterile conditions, and the preparation should be made free from organisms, free from growth of all the types of organisms. That means all such additives, it may be acid, it may be base, it may be buffer, it may be anti-foam agent, or it may be intermittent addition of any nutrient medium. So all these additives should be sterile. Maintaining aseptic conditions during the fermentation process is all these are the most critical parameters which needs to be monitored to avoid the contamination during fermentation. Now, medium sterilization. Medium sterilization, medium means it is a liquid medium which is present, which is prepared in the solvent water. So aqueous medium. So there are several ways of sterilization of this aqueous medium. Filtration, radiation, ultrasonic treatment, chemical treatment, and heat. All these are the different methods that can be used for sterilization of aqueous medium. Out of these list of ways of sterilization, steam, which is generated from water, it is used universally for the sterilization of fermentation media. That is because of its high penetration power. However, it should be considered whether to use steam as a sterilizing agent or not, and it is dependent on the composition of fermentation medium. If the fermentation medium contains certain heat sensitive medium components, then steam is not a good choice for the sterilization. So instead of that, the other techniques such as filtration can be used for the sterilization of medium. So such fermentations are, for example, in case of media for animal cell culture. So in this case, filtration will be the method of choice, as such media are completely soluble and contain heat labile components. After this brief introduction to the process of sterilization of industrial medium, let us try to understand the kinetics of sterilization. Kinetics means happening. the way a particular event happens, the process of happening, the event, it is called as kinetics. So what are the steps, or what are the events that happen during the sterilization? What happens during the destruction of microorganisms? The microorganisms are not destroyed at once, so they are destroyed in steps, they are destroyed in stages. So we need to understand all these stages and steps, so which is possible through understanding the kinetics part. So that is the meaning of kinetics of sterilization. Under this, we'll be understanding the concept on derivation of Dale factor also. The destruction of microorganisms by steam or moist heat. As I mentioned earlier, steam is universally used as a sterilizing agent for the sterilization of medium. In case of some exceptions, filtration is used, but majoritarily steam is used. So we'll understand the kinetics of sterilization by considering sterilizing agent, that is moist heat. When the sterilization is done, there is a reaction that occurs during sterilization. That reaction is destruction of microorganisms, and these microorganisms are destroyed by moist heat. So it is like a chemical reaction. It is like a first order chemical reaction, which says that as the temperature of the system increases, the rate of reaction increases. So that can be truly applied to this sterilization process, because in this case also, as the temperature increases, the rate of reaction increases. What is that reaction? That is destruction of microorganisms. So if as the temperature increases, the rate of destruction of microorganisms increases. So there is an exponential relationship between time, temperature. Therefore, we call it as a first order chemical reaction. It can be represented in the form of this equation, equation number 1. That is, what is this reaction? Destruction of microorganisms by moist heat. It can be explained in terms of equation minus dN by dt is equal to Kn. In this equation, N is the number of viable organisms present in the medium. T is the time of sterilization treatment. Sterilization treatment means, suppose we have 121 degrees Celsius temperature. So we sterile our medium at 121 degrees Celsius for 15 minutes. So 15 minutes is the period of sterilization treatment. That means it is the time required, it is the time of exposure of medium to that particular temperature, that is T. K is the constant, which is called as reaction rate constant of the reaction, or in this case, in this reaction of destruction of microorganisms, we can call this K as the specific death rate or the death rate constant. Now, further we'll expand this equation. On integration of this equation number 1, the equation will be converted into equation number 2 as Nt by N0 is equal to e raised to minus Kt. So in this equation, N0 is the number of viable organisms, means these are the contaminants, number of viable organisms present at the start of sterilization treatment. That means it is the initial number of contaminants present in the medium. NT is the number of viable organisms present after a sterilization treatment period T. Means this is the final number of viable organisms after sterilization treatment period T. So in short, N0 is the initial number of contaminants, viable organisms, and NT is after the application of sterilization treatment, the final number of viable organisms. Now, if we take natural logarithm of equation 2, it will be reduced to equation number 3, which is like natural log, that is ln of nt by n0 is equal to minus kt. Graphical representation of this equation number 3, it can be seen in this plot. So viable organisms number, it decreases exponentially. Exponentially means step by step over the treatment period. That is the time required for sterilization. So a plot of natural logarithm of n is the number of viable organisms, that is ln n against time t, it will yield a straight line and the slope of which will be equal to minus k. Let us see what is this graph. This graph is called as thermal death curve, which is like this. So this is a graph of log of n, natural log of n against sterilization treatment time t. So this graph shows a straight line that is in inverse proportionality between log of n and t. Therefore, the slope of this straight line will be in negative, that is minus k. So now if we have this graph in which a microbial suspension, that is fermentation medium having contaminants, is exposed to a fixed temperature, sterilization temperature, for definite period of time. So this will be the picture. From this graph, what we understand is, if we go for calculating the slope, that is k, how do we calculate slope? By the equation y2 minus y1 is equal to x2 minus x1. So in this graph, what is y2? Y2 is this, the initial number of microorganisms present. What is y1? Y1 is the final number of microbes present after the sterilization treatment time t. X2 is this, x1 is this time. So final time minus initial time. So this is how the equation is. Y2 minus y1 is divided by x2 minus x1. Now we'll replace the real values. What is y2 exactly? Y2 is initial number of viable cells present, that is log of n0. What is y1? Y1 is the viable organisms present after sterilization treatment period t. So it will be log of n T divided by x2 minus x1. So x2 minus x1 is sterilization treatment period, that is time, the time required for sterilization. So that is T. Now we'll rearrange this equation, that is ln n0 minus log of nt divided by t. So after rearranging this, it will become kt is equal to log of n0 minus log of nt. Further, kt is equal to log of n0 by nt. Further conversion, it will lead to the equation number 3 as we have seen in the previous slide, that is log of nt by n0 is equal to minus kt. That is how the final equation is. This is how we derived an equation 3, that is minus kt is equal to log of n0 by nt, which explains us the concept of del factor. This is how we derive this equation number 3. There is another way by which we can derive this equation. If we consider the same graph, that is thermal death curve, log of number of viable organisms versus time at a fixed temperature, that is 121 degrees Celsius temperature, for example. So the equation for this line will be y is equal to mx plus c. It is a straight line equation. So in this case, now we'll replace it with the real values. So therefore, y means it is log of nt. Log of nt is equal to m. M is the slope minus k. X is t, time, plus log of n0. Now you can see here, let me go back. This point, this is log of n0, that is, it is the value of c. C is what? Intercept, the value of intercept on y-axis. So the value is n0 because it is the initial number, and this is the value of nt, that is log of nt, that is t means time, nt means number of viable organisms present after sterilization treatment period t. This is how we can write this equation. Further, this equation will be rearranged. Therefore, log of nt minus log of n0 is equal to minus kt. Further rearranging this equation, it will lead to equation number 3, that is log of nt by n0 is equal to minus kt. So these are the two different ways by which we can express or we can derive this equation number 3, either by the method of previous slide or by the method of this slide. Equation number 3, after rearranging this, we'll get this final equation, that is kt is equal to log of n0 by nt. This equation is very important in order to decide the sterilization protocol. Now, this value of k, this value of k is specific death rate. Now specific death rate of whom? Specific death rate of contaminant. I'm using the word contaminant and not contaminants. That means we are talking, when we talk about contamination, we talk about only a single species of contaminant. So this value of K, it differs from species to species of contaminant. So this value of K, that means specific death rate of Bacillus will be different, specific death rate of Staphylococcus will be different, specific death rate of E. coli will be different. So this value of K, specific death rate at a fixed temperature, will be different for different organisms. So this value of K is species dependent. Second thing is that this value of K is not only species dependent, it is also dependent on physiological form of the cell. Physiological form means, say for example, in case of endospore producers, there will be two physiological forms, a vegetative cell and an endospore cell. So the organism is one, but it exists in two forms, vegetative cell and endospore. The difference will be that vegetative cells are sensitive to temperature, endospores are not. So therefore, their K values, specific death rate of vegetative cell, will be different from specific death rate of endospore of the same organism. So what we learn from this kinetics? So from kinetic description, it can be concluded that after a certain time means T, certain time of sterilization, there will be less than one viable cell present, which indicates sterile conditions. Sterile conditions are indicated by NT is equal to 0. That means the number of contaminants present after sterilization treatment time T is 0. It indicates complete sterile conditions. So whatever was the number of N0 after sterilization treatment time T at fixed temperature, finally we don't have any viable cell present in the fermentation broth. That means the value of NT becomes 0. So NT equals to 0, it indicates sterile conditions. Is it that simple to understand or to consider? No. The value of NT is never considered as 0. Value of NT has a significance. It is very important. So instead, this value of NT is considered in terms of probability of an organism surviving the treatment. That means we never be assured that the conditions are sterile. What we think is that there is less than one organism present in fermentation broth, which indicates the risk of contamination. So this value of NT is considered in terms of probability of an organism surviving the treatment. That means we consider that there are few microbes present even after the sterilization treatment. Say for example, if it were predicted that a particular treatment period, that is T, reduced the population to 0.1, that means whatever is the value of N0, so that value of N0 is reduced to NT. that is 0.1. So if we consider that the value is reduced to 0.1, what does it mean? It means that NT equals to 0.1. This means that the probability of one organism surviving the treatment is 1 in 10. How is this? 0.1 is what? 0.1 is 1 by 10. So what is this 1 by 10? The chances of surviving of one organism is 1 in 10. This is called as a risk of contamination. We can consider this like that. If there are 10 batch sterilization processes, so it indicates that out of 10 batches of sterilization, there is a risk of contamination of one batch. This may be better expressed in practical terms as a risk of one batch in 10 becoming contaminated. Let us take another example. If we consider the value of NT as 0.01, 0.01 is what? 1 by 100. So what is the risk of contamination? It is 1 in 100. It means that there are chances of contamination of one batch out of 100 batches. If it is 0.001, then it will be 1 by 1000. That means there are chances of contamination of one batch out of 1000 batches. This is how we consider the value of NT in terms of probability of contamination, chances of contamination, risk of contamination. So while calculating the time temperature schedule for sterilization of medium, we never consider the value of NT as 0. We consider the value of NT as 0.1, 0.01, 0.001, 0.0001 likewise. So log of N0 by Nt as per equation number 3, it is called as Dale factor or Nabla factor, or it is also called as sterilization criterion. Sterilization criterion word is very important because this is the factor which is used for scale up of sterilization. This is the factor which is used to decide time temperature relationship in order to sterilize the medium. That is why it is called as sterilization criterion. So Dale factor, it is used as a criterion for the design of sterilization procedure. What is the meaning of designing of sterilization procedure? It is deciding time temperature relationship at a given fixed sterilization temperature. That is called as sterilization procedure. So Dale factor is very useful in the designing of sterilization procedure. It is abbreviated by this symbol. Therefore, Dale factor, we can define it like it is a measure of fractional reduction in viable organisms count produced by certain heat and time regime. Regime means the area, time temperature relation. Therefore, Dale factor, now we'll put the value of Dale factor in equation number 3. So it will be del factor is equal to log of n0 by nt, or it will be del factor equals to kt. This equation is very useful for scale up of sterilization, for design of sterilization procedure. Therefore, you need to remember this equation, which is very easy. What is the significance of this kinetic descriptions? So this kinetic description of bacterial death, it enables the design of procedures giving certain del factors for the sterilization of fermentation broth. So we can calculate the del factors, and accordingly we can decide the time temperature relationship. The time of exposure, we call it as holding time of medium at desirable sterilization temperature. For batch sterilization, it is 121 degrees Celsius. It can be calculated considering the required del factor. So we'll learn this using an example in next few slides. Therefore, the degree of sterilization, that is del factor, it may be obtained over a wide range of time and temperature regimes. Time temperature regimes means if you are using very high temperature, then the time of exposure, the time required for sterilization will be decreased. If we are using comparatively low temperature for sterilization, for example 110 degrees Celsius, then the time of exposure is going to be increased. So that is the meaning of wide range of time and temperature regimes. This means that we can obtain same degree of sterilization using different time temperature combinations. Same degree of sterilization may result from treatment at high temperature for short time as from a low temperature for long time, as I explained you earlier. Now again, going back to the value of K, that is a specific death rate, we have seen that it is dependent on species, it is dependent on physiological form of cell. For example, endospore, which is in case of bacillus. So endospores are more heat resistant as compared to vegetative cell. Now, to apply these kinetic studies, it is necessary to know thermal death characteristics of all the microorganisms, because we never know which is your contaminant, which organism is causing contamination. So it is essential to know the thermal death characteristics of all the microorganisms, which is practically highly impossible, because we cannot spend that much of time in determining the thermal death characteristics of all the organisms. So considering this difficulty, what we assume? We assume that there is a single contaminant, and what is that contaminant? It is the most heat resistant contaminant present in the fermentation broth. So we assume that the contaminant present in fermentation broth are spores of Bacillus stereothermophilus. Why spores of Bacillus stereothermophilus? Because it is the most heat resistant organisms. And why spores? Why not vegetative cells? Vegetative cells are heat sensitive. Endospores are heat resistant. So these are taken as the indicators for the sterilization treatment, that is spores of Bacillus stereothermophilus, the most heat resistant form, which is used as a sterilization criterion. Therefore, by assuming Bacillus stereothermophilus as the design organism. What we are designing? We are designing the sterilization process. We are deciding the time temperature relationship. That is, we are designing the protocol of sterilization of fermentation medium. So for this, the studies should be based on Bacillus stereothermophilus as the design organism for the process, for the proper and actual and precise determination of sterilization process. Now, one very important thing, it should be remembered that Bacillus stereothermophilus is not always adapted as the design organism. If the most heat resistant organism contaminating the medium in that fermentation industry, if it is known, then thermal death characteristics of that organism should be determined, and that heat resistant contaminant should be used as the design organism. So that considering that organism, it may be advantageous to design sterilization process by considering that frequent contaminant.